from here on out, the rest of this should be really familiar to you from first year chem. I'm hoping that you've done some work with orbital diagrams and electron configurations. The quantum number stuff is pretty awesome. It's going to give you sweet dreams at night. It lets us locate, to the best of our ability, an electron. However, in the scheme of things, I don't want to know where just one electron is located. I kind of want a map of where all the electrons in an atom are located. And I don't really want to have to do like 15 sets of quantum numbers if I've got, like phosphorus with 15 electrons. So orbital diagrams and electron configurations give us a better visual map as to where all the electrons may be located in a particular atom. I'm not saying that quantum numbers aren't cool and useful. They are. They're great. But I think these might be more useful. I really do enjoy orbital diagrams for a few reasons. These orbital diagrams will kind of show us like all the electrons, how they're distributed within the orbitals in order of low energy to high energy. This is referred to as the Aufbau principle. For those of you that are fluent in German, Aufbau kind of means to build up. So we're going to always fill orbitals from the lowest energy level up to the highest energy level. And this is super easy, piece of cake. You find your beryllium on the periodic table. Beryllium is element number 4. So I need to map out the 4 electrons in beryllium. So we start with the 1s orbital. The 1s orbital holds 2 electrons, and I can't move up to higher orbitals until I finish the 1s orbital. Now those 2 electrons, if they're paired together, would spin opposite. So you may recall that we put 2 arrows in the box, and we show them pointing in opposite directions. And that should refer to the 2 electrons that would fill the 1s orbital, spinning in opposite directions. Next, I go to the 2s. The 2s orbital can hold 2 electrons. They would spin opposite. There we go. Here's the 4 electrons in beryllium. 2 of them in the 1s, 2 of them in the 2s. The other thing that's kind of nice is that this shows us the order that the orbitals fill. The first energy level only has an s orbital. That's it. Then I go to the second energy level. I'll have an s, and I'll have the 3p orbitals. Now the p orbitals are a little bit higher in energy, so they're shown a little bit higher than the 2s. But of the 3p orbitals, they are all equal energy. So the p orbitals together are all kind of shown on the same level. These guys are all equal energy, but they are higher than the 2s. That's it for the second energy level. Next, I would go to the third energy level, where I'll find an s. I'll have the 3p, and that's the first time we find the d's. There are 5 of them. They're all equal energy, but they are higher in energy than the s or the p. Now you may know this notice this discrepancy here. You would sure think that the 4s would be higher in energy than the 3d, right? It's a bigger orbital, so the electrons are further from the nucleus. That should mean they're higher energy, they're less stable. Yeah, they're not. And we'll kind of mention this when we get into the periodic table and some trends a little bit. Here's the deal. Let's say you are, you're a boxer. Oh, this is going to be a great scenario here. You're boxing. You've got 2 choices for opponents. You could pick one guy, but he's a big guy. So I don't know, he's like really tall and beefy. But there's just one opponent. It's just a big guy. So here's the deal with the 4s. It's just one orbital. It's a big orbital. Would you rather fight that guy, or would you rather go against 5 guys? They're these d orbitals, high energy. So you've got 5 guys that are all like souped up on, like Mountain Dew and Pixie Sticks, so they're going crazy. They're a little bit smaller, but there's 5 of them. And they're like high energy guys. They're going all around the place like punching like crazy. So you've got to decide, who would you rather go up against? 5 crazy high energy wild guys? Or one guy that's just kind of big and beefy? Well, in the end, it turns out that those 5D orbitals do carry more energy than the 1,4s. So even though I get it, like the 4s is a bigger orbital, the electrons can be a little bit further from the nucleus, but because it's just an s orbital, if you take both into consideration, that 4s carries less energy than the 3ds. So it's kind of like opposing forces that, well, the d orbitals are higher energy than an s, but the 4th energy level is higher than the 3rd. The 3ds kind of win out. They carry more energy. So that's why when you see these orbital diagrams, the 4s will be like kind of sunk down a little bit, just because it does carry a little bit less energy than the 3ds. And we'll deal with that when we get to the periodic table a little bit. Let's do carbon. Carbon is element number 6. Excellent. So we're going to do 6 electrons. We got to start with the lowest energy level. 1s gets 2. Whoa. 1, 2. Spinning opposite. That's it for the first. Second energy level, we got the 2s. 1, 2. Okay, now you might remember this thing called Hund's rule. Hund's rule refers to orbitals of equal energy. Orbitals of equal energy. This is referring to like p orbitals or d orbitals or f orbitals, although we probably won't be doing this with f orbitals. Okay, for example, now I have 4 electrons, I need 2 more. Carbon is element number 6. I'm going to put those 2 electrons in the 2p orbitals. It's most stable to fill those p orbitals 1 electron at a time before pairing them. So for example, this is wrong. Let's say that these are the p orbitals. La 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 la. Those are the 2p orbitals. We would not do this. 1, 2. That's a sad face. That's bad. Here's the deal. I've got 2 electrons that I need to put in orbitals. I have 3 available orbitals. Why would I pair them? There's going to be something going on here called electron repulsion. These electrons are both negative. Like charges repel. They don't want to be in the same orbital if I don't have to pair them. Now in an s orbital they have no choice. It's like, I don't know, you have a 1-bedroom apartment. You have to share a bedroom. But now let's say I've got, I don't know, 3 kids. Or I should say 2 kids and 3 bedrooms. I got 2 kids and 3 bedrooms. Well, let's say they don't like each other. They're going to fight. Why would I make them share a room? We're going to give them their own. Now, it doesn't matter if you make these arrows go up or down. That is totally arbitrary. You could have 1 up and 1 down. That would be fine. As long as within the same orbital they're paired. But here's this Hund's rule that says when you get to equal energy orbitals like p's and d's, fill them 1 electron at a time first before pairing them. Now sometimes we have no choice, we have to pair. If I had 1 more electron, the 7th electron would go in the other empty p orbital. But if I had an 8th electron, I'd have to go back and pair it. For example, let's look at sulfur. Sulfur is element number 16. So here we go. We're starting from the bottom. 1, 2, 3, 4. Technically, I would fill this 5, 6, 7. but I cannot go up to higher orbitals until I completely fill the lower energy orbitals. So sorry guys, now you have to get paired. 8, 9, 10. 11 and 12 will go in the 3s. We have to fill the s. And now I'll go to the p's. This is going to be electron 13, 14, 15. Sorry guys, somebody's got to get paired for 16. And again, it doesn't matter which one you would pair. If you paired the middle one or you paired the one on the end, it's totally arbitrary. That doesn't matter. It doesn't matter if your single electrons are going up or down. You could have one up and one down. As long as within an orbital, they're spinning opposite. So again, it's kind of like now when I look at this 3p, it's like I have 3 bedrooms and 4 kids. Sorry, somebody's going to have to share. Now, will that cause a little tension? Quite possibly. Ooh, we may have to talk about that later. There will be a little electron repulsion when you've got electrons sharing an orbital. And that might affect some of the properties of these elements. We'll deal with that later. So I'm hoping that this is somewhat familiar to you. The Aufbau principle just says that we always fill low energy to high energy. We have to completely fill a set of orbitals before we can move up to higher energy orbitals. And Hund's rule says that when you get to p's or d's that are equal energy, fill them one at a time first. Then go back and pair them. And this is, again, something that they're going to do to try to trick you. That as a wrong choice, let's say this was like multiple choice, they might do this. 1, 2, 3, 4. And you would not be tricked because you're super smart. You'd say, no, that's not right. If I can, I need to give those orbitals their own, or those electrons their own orbital, because like charges will repel. Now here's one thing that we should mention. This is a little more AP. We could have atoms with electrons that are excited. And we mentioned this term excited state earlier, that it just means that an electron has gained some energy and is temporarily in a higher energy level or a higher energy orbital. For example, hydrogen has 1 electron. It would normally be found in the 1s orbital. So if I had, let's say 1s, that would be the ground state. Hydrogen would normally put his 1 electron in the 1s orbital. What if you saw something like this? Yikes, that's weird. Okay, we would still know that it's hydrogen. There's only 1 electron. Hydrogen is the only atom that has 1 electron. But we would say this is excited hydrogen because that electron is not in its normal ground state. Same thing could happen with something like oxygen. And again, some of this could be kind of arbitrary. Oxygen is element number 8. So we would go like 1, 2, 3, 4, 5, 6, 7. Whoa, what's that? That's nuts. This would be something good for a multiple choice question where they might say like A, B, C, D. Which of the following is the electron structure of oxygen in an excited state? Well, number 1, I'd be looking for 8 electrons. 2, 4, 5, 6, 7, 8. But I'd be looking for those electrons to not all be in the correct order. One of them, or maybe more, are temporarily at a higher energy level than they should be. That would be excited oxygen. Cool. Oxygen in the ground state would have a paired p electron. Now the last 2 terms that we should briefly mention when it comes to these orbital diagrams are 2 that, they're kind of annoying because everybody gets them mixed up. Diamagnetic and paramagnetic. We can do a little demo with this in class. Diamagnetic means that all the electrons are paired. Now here's what's confusing. Paramagnetic means that you have unpaired electrons. People get these flip-flopped. because they want to say paramagnetic means the electrons are paired. Nah, dang, that's the opposite. So I kind of remember it this way. Di means two. Di is the prefix for two. Dimagnetic means that the two electrons, or I should say all the electrons in an atom, are paired. Paramagnetic, I think of unpaired. So remember that these are not what you would expect. Paramagnetic means that the element has unpaired electrons. Dimagnetic means that they're all paired. So for example, if I look back at something like beryllium, beryllium has all of its electrons paired. So we would say that beryllium is dimagnetic. Carbon does not have all of his electrons paired. We could call carbon paramagnetic. Oh, that's not so bad. And again, this kind of has to do with some of its properties that we can look at as a demo in class. But you kind of have to think about the orbital diagram. This is where I do kind of like these orbital diagrams. Are the electrons paired or are they unpaired? The only way that you really know that is by thinking about how they're distributed amongst the orbitals. And where I really have to kind of think twice is when I get to like p orbitals or d orbitals. You know, something like carbon. He has an even number of electrons. They are 6. So sometimes mistakenly people will say, oh, dimagnetic, because you know it's an even number. They must all be paired. Ooh, but they're not. 2 of those electrons are in their own orbitals. So to figure out the magnetic properties, you really do have to think about the electron distribution as an orbital diagram.